Hi, I'm Sanjuan and I'm going to talk about the LISA telescope testing at the University of Florida. The telescopes in LISA are used to send and receive light between the spacecraft, and they are part of the science interferometer, which means that they have stringent requirements. Probably the most important one is the picometer square root of Hertz stability requirement. There are other ones, such as the micrometer stability requirement over the mission duration or the subpar per billion backscatter of the transmit laser power. The LISA telescope prototypes will be delivered by NASA, and they will be tested at the University of Florida for the dimensional stability and straight line requirements, the backscatter requirement. I'm going to give a short overview on the efforts at the University of Florida towards these measurements, but there are two other talks about this topic, one by Soham Kulkarni and one by Ada Uminska, both from the University of Florida. The in-band length stability requires picometer measurements in the LISA band. This is between 0.1 millihertz and 1 hertz. To do so, we're going to build an optical cavity around the telescope and lock a laser to it. This is what is shown in the drawing, where we have the telescope inside the telescope test structure, and then we're going to lock another laser to a reference cavity, and we're going to compare the frequencies of both lasers, and that signal gives us the information about the telescope stability. This is something we've done in the past, and it's a clear concept. However, with the telescope inside the cavity, that poses important challenges. So first, the telescope structure, test structure, needs to be at least as stable as the telescope itself. This is something that Soham is going to talk about in his presentation. The telescope will also have optical losses. The requirement for the optical efficiency is on the 95%. That means that we're going to have a low finesse cavity that creates problems on the boundary of hole locking scheme. We're going to have also important problems or issues with the cavity design and alignment. This is something that Ada is talking in her talk, and this is essentially because the telescope has this huge magnification of 134. We're going to have also the thermal stability requirements that we have to reach a microkelvin square root of Hertz stability, and we also have to deal with the size and the weight of the telescope, which is almost 1 meter long, 0.6 meters wide and tall, and can be almost 40 kilos in weight. The long-term stability measurement is similar to the in-band measurement, but here we're going to use an absolute frequency reference, an iodine cell, instead of an optical cavity as a reference. We're going to compare the telescope cavity to a laser lock to the iodine cell. And we're going to take a few measurements per week over a period of 3 months with an accuracy of 25 nanometers, which is equivalent to roughly 1 micrometer over 10 years. We're going to also monitor the temperature correct for CT effects, because the goal is to measure non-thermal effects over time, anything inherent to the material of the telescope. And here on the right-hand side, you see the schematic of the setup. The current work at UF, we're focusing on measuring stability of what we call proto-telescope test structures. So here you can see a couple of photos. So these are a scaled down versions. So instead of being 1 meter long, they are about 25 centimeters. And here you can see two designs. One on the left-hand side, it's a full ULE proto-telescope test structure. And on the middle, you see a hybrid design where we have SuperInvar and ULE. And on the right-hand side, you see a plot showing stability measurements of these configurations. And Soham is giving all the details about this in his talk. But you can see that we can reach picometer stability in almost all the frequency band. We're also working on the designs of the final telescope test structure in CAD models, and how we can accommodate the telescope inside this structure, and how the whole thing can be placed inside the vacuum chambers. This is shown here in these drawings, these CAD models. And we're also working on these AutoCAD simulations to define the optimal optical cavity where the telescope is going to be sitting in, and how we set requirements on alignment tolerances and establish alignment procedures, because it's a non-trivial problem given the telescope and its large magnification. So that's what Ada is talking about in her presentation. So check that. We're also working on the thermal setup of the vacuum chambers. So we want to measure the picometer stability at different temperatures between 15 and 30 degrees. At each of these temperatures, we want to have a stability at the microkelvin square root of Hertz. And to do so, we plan to have some cooling jackets wrapped around the vacuum chamber that will be kept at 15 Celsius. with insulating layers around it, and then inside the vacuum chamber 2 layers of thermal shields with large Kaplan heaters that can enable an active temperature control. Here you can see a drawing of the concept of the thermal setup. On the right hand side you can see photos of the vacuum chamber, and on the top you can see some simulations where we can see the thermal stability expected inside the vacuum chamber. Finally, we're also working on the setup for measuring backscattered light. The plan is to measure the back reflection from the telescope using a heterodyne detection scheme, where the goal is to measure sub-ppb attenuation levels. The setup is now being tested and calibrated, and the concept is here on the right hand side. We have 2 lasers that they are phase locked with a frequency of a few megahertz. And yeah, by detecting the amplitude of the bit node between the local oscillator and the laser that goes through to the telescope, that we can infer the amplitude of the backscatter light. And here on the left hand side you can see a measurement just to see the floor noise levels, and with this kind of measurement it's easy to reach femtowatts with 1 milliwatt for the local oscillator. So the planned test, it's here. We will start in 2022 with the first engineering development unit. We'll test the picometer stability at different temperatures between 15 and 30 degrees. We'll try to also measure the CT and the backscatter light, which should be a quick and easy measurement, hopefully. And then in 2022, once we're done with this prototype, we'll send it back to Goddard, and then we'll receive the second prototype, EDU2, Engineering Development Unit 2, in 2023. And we'll do the same, picometer stability, CT determination, backscatter light, and on top of that, we'll do the long-term stability test. So by the end of 2023, these 2 EDUs should have been tested, which should be a big step towards TRL6. So conclusions and further steps is that the LISA telescope ground verification testing, it's under development at UF. The main goal is the picometer stability measurement, which is a key towards TRL6. In addition, we plan to measure long-term stability, CTEs, backscatter light. And currently we're testing downscale telescope test structures. We're evaluating the optical parameters for the cavities to build around the telescope. We are defining the mechanical tolerances and alignment procedures of the setup. We are also designing the full-size telescope structure in CAD models, and we are characterizing the noise of our setup, which is important once we have a low finesse cavity. And that's all. Thanks for your attention.